Welcome to the Interface program. Today we have one of the most eminent scientists and a science administrator, Professor Suresh Das, with us to discuss about science, particularly with respect to chemical sciences, its state of affairs, and how the students can build a career in science in India. Welcome, Professor Suresh Das, to this
Thank
program.
you, Ravi. Thank you for the, and I'm indeed very happy to be here to participate in this interface, and I look forward to this interaction.
Now, I was looking at your biodata. It is a great CV, and you have a great career in science. I learned that you studied in Pune, Delhi, and interestingly in the erstwhile Baghdad University in 70s for your masters. Then you are in Newcastle on time, and for your PhD. Then you have worldwide experience in Germany, Max Planck Institute, and in University of Notre Dame, US, before you came back to India to join the Tata Institute of Fundamental Research as a scientist for a short while, before moving to RRL Trivandrum as one of the pioneers in building the photosciences division in Thiruvananthapuram. And it's actually a wonderful career in science. For a young person now who is a student who is looking at science as a career, what motivated you to take up a career in science? How did you actually do it?
That's a very interesting question. Ravi, I've been actually very fortunate. I've always encountered very wonderful teachers throughout my life. If you talk about, you mentioned that I studied in Pune, and that was where I did my high school and my college undergraduate degree. Both places I had wonderful chemistry teachers, and I especially remember Sir Dhawale, as we used to call him. He was, he used to teach us with so much of excitement, and he never stuck to just what was in the textbook. Even outside of the classes, he would discuss with us on various aspects which were not really part of the curriculum. I remember on occasions he was talking about the chain reactions that happen and also polymerization, also light initiated reactions. These were all very fascinating to me, and that is what instigated me to want to follow up a career in science. Then, as I mentioned, subsequently I went to Ferguson College in Pune. There also we had wonderful teachers. I remember one organic professor, Pathak, was who inspired me a lot. And you mentioned that I was also in Baghdad. There also, I met Professor Ghazi Darwish. I would like to mention his name because he was the one who really directed me who recognized the fact that I could contribute something into science. He was a spectroscopist, and he was fascinated that I was coming from India, which was very rare for a University of Baghdad to have a student from India. And he was also, he was an admirer of C.V. Raman, and thinking that I'm coming from the same country. So he treated me with great appreciation, and he sort of saw me as a scientist, which I never saw in myself at that time. So the inspiration from all these teachers is what directed me to take up a study in science and follow up on a research career.
And when I looked at this thing, when you returned to RRL Trivandrum, I think it was the laboratories were almost rudimentary in those times. And you could really come up as one of the most talked about scientists in photosciences in this area. So particularly photoscience requires a lot of instrumentation, a lot of facilities. How do you actually see that evolution?
Yeah, again, there also I must say I was very fortunate. Yeah, I'm sure you have heard about Professor M.V. George. He had retired from IIT Kanpur. He had moved to then RRL Trivandrum. And he was an inspiring person, and especially for me, coming back after a long stay abroad and trying to find my feet here in the research environment in India, this was very helpful to have somebody like Professor George again as a mentor. I think this is something that young scientists need to remember, that the role of a mentor in building up a science career cannot be underestimated. You can't speak enough about it. So as I said, we had good teachers. Then I had Professor M.V. George there, and we had a small group, enthusiastic group, there. And as you correctly said, the kind of facilities that was available for photochemistry was not there, but that was what inspired us. And with the kind of we had to write to proposals, we had to recognize what was needed. One thing that we did was we looked at some of the best photochemistry groups around the world, the kind of research they were doing, the kind of facilities that they had. There was, I remember specifically looking at the Boston University, the photonics department. So that was kept as an aspiration, and to see how we could build our photochemistry group into that kind of level. So we started slowly, it took some time, but eventually it grew up into one of the best photochemistry groups in the country, as you would know.
Professor Das, I was actually looking at your research and photoresponsive materials particularly. Can you briefly, in simpler terms, explain to a graduate student what actually it means to say photoresponsive material?
Yeah. So, photochemistry, of course, all of you are familiar that it's a chemistry that is initiated by light. But when we talk about photoresponsive material, there are examples of it all around the world. Where, for example, if you look at photosynthesis, where the plants use light energy to convert it into a chemical energy, or even the whole process of vision, how we see. All of these, the initial reaction is a photochemical reaction, which is followed up by several processes, chemical processes, and which actually leads to the final event. And so basically photoresponsive, so what we were trying to do when we tried to design photoresponsive materials was to take inspirations from nature, see if we could design some materials which in my particular case, I was interested in a group of molecules, compounds called liquid crystals. So liquid crystals have a certain property, and what we found was that we could actually design liquid crystals which could respond to light, which could undergo photochemical reactions. And so the idea of photoresponsive liquid crystal from our side was to see if we could design a material which is a liquid crystal which can absorb light and undergo a chemical transformation. When that chemical transformation happens, because the liquid crystal, the structure of a liquid crystal is so much dependent upon the shape of the molecule, photochemically we were able to change the shape of the molecule. And when the molecule shape changes, it is no longer a liquid crystal. So you are bringing about a phase transition using light. So this has many implications, because you can imagine you're actually using light as a switch. It can you can use it to design different kind of mechanical actuators, and also for display systems, for recording images. So this is what was one of my major areas of research. And the other aspect, of course, on liquid crystals is there is a specific type of liquid crystals which are termed as cholesterics. These are specific liquid crystals where the molecules align in a helical fashion. And what is interesting about that is because of the helical fashion, they have a structural pattern, and that leads to Bragg reflection. As you would know, in Bragg reflection, yes, you get different kinds of colors depending upon the spacing of the layers. And this is again something you will see. For example, if you look in nature, we have different kinds of colors. You have flowers having some kind of which use pigments. But when you look at something like a butterfly, if you look at the color of a butterfly, it is not based on pigments. It is, if you look at under the microscope, you will see that the butterfly wings has some very specific structures, which is periodic, and this gives rise to Bragg reflections, and that is what gives rise to these colors. So liquid crystals are also some materials which can align in the same manner, and it can give rise to different colors. Now what we found is that if we incorporate some photoresponsive materials into that, then using light we are able to bring about a change in that color. So therefore you could actually do color recording, and that is a device that we had invented and which was patented in our laboratory.
In fact, for a graduate student, we actually say plants are photoresponsive.
Yeah.
Like the trees and all, they will actually move towards sunlight.
Yes.
And so this is again, it's a photoresponsive.
That is a photoresponsive material. That is why I said in much of our inspiration is found from nature. And the plants, of course, the mechanism is very different. If you really look at how the plants move towards light because of the sun, It's based on a fundamental process is a photoelectron transfer process. But that is, but we get the idea from that. And one of the things that we learn from nature is that if you really want to design a photoresponsive system, we have to think about amplifying the photochemical reaction. Because you know that at best one photon can give you one molecular transition, and that's 100% reaction. And that is not sufficient. That needs to be amplified if you really want to have a material of with any significant property. And nature finds very significant ways of assembling molecules around this initial photochrome or photoabsorbing molecule, and use that transition to bring about substantial changes in the self-assembly. And that is, the liquid crystal plays that role. The liquid crystal plays the role of the self-assembly that you see in nature. And that is what leads to the dramatic effects that you see in terms of plants moving, phototropism, that is, you mentioned plants moving towards sunlight, or you talk about, as I mentioned, photosynthesis, very highly efficient at the fundamental process. Although the overall efficiency may be less because you're talking about other subsequent reaction. But the photochemical part is very, very almost 100% efficiency. And so the photochemistry combined with self-assembly is what makes things work in nature, and that is what we were trying to mimic to some extent in the lab.
That's something which I was very much interested. We all talk about photosynthesis, where nature easily converts this light energy into chemical energy. Now, how far away are we from artificial photosynthesis, mimicking nature?
I think when you look at it, this is an area of research which has started long ago. I think we have made substantial progress in this. When you look at, for example, the solar cells, it is, and especially when you look at the newly designed solar cells which are based on organic materials, those are actually mimicking the idea of what we see in photosynthesis. So the kind of molecules that people design in terms of trying to harvest light energy, then bring about that fundamental charge separation, and in the case of plants, it is of course to store that energy as chemical energy. But what we are doing in the laboratory is trying to develop photoelectrochemical cells. Okay, so that is the idea, is that of photovoltaics. So this is basically, if you look at it at the fundamental level, we are mimicking, and you have seen now that the efficiencies of many of these photovoltaics, especially the organic photovoltaics, are improving dramatically. And so it will not be very long before we actually see, we are actually already starting to see some applications based on this. Yes, and of course there is also the possibility of directly splitting water from using sunlight. This is a kind of an ideal photocatalytically, and that is something that of course people are working. The efficiencies are slowly improving, and I can see that in the near future this can become actual technology.
Yeah, great. I mean, I was so fascinated with many of your contributions in this area of these basic sciences, particularly in these photosciences. I think you are also a director of the National Institute for Interdisciplinary Sciences in Thiruvananthapuram, and later you are also, as an administrator and as the executive vice president of the Kerala State Council for Science, Technology, Environment, where you had both administrative and managerial science management in the state. Now, there is people always say there is a huge gap that is existing between the laboratories and the industrial applications of basic science, say for example. How easily it gets translated into something for the society. How do you see actually this gap in between basic science, applied science, and industrial science?
Yeah, it's a kind of a complicated question because it requires really an elaborate answer. But things have been changing if you really look at it. There was a time when Louis Pasteur said that there is no such thing as basic science and applied science. There is just science. You have to compare it with a tree. If it's like a tree, you nurture the tree, and the fruits will follow. So Louis Pasteur also used to say that you nurture the tree of science, and the applications and the technologies will flow. And that was how it used to be in the past. If you look at the fundamental research in terms of electron spin, which actually led to the MRI today, you can see it took almost 100 years for that to happen. But today there is a feeling that we need to translate research that is being done in the laboratory more rapidly into technology. And so this is something that requires an active cooperation of not just the scientists. You can't just tell the scientists that, make your science applied research applicable, because what drives the scientist is fundamentally his curiosity, and he wants to do something that is original. So in order to capture that originality, original work, and make it of some application into society, you need an entire ecosystem that supports that kind of translational research. And translational research, for example, the government has to support it, the industry has to become a partner to it. And you will see in many of the advanced countries, if you look at where innovation levels are very high, if you look at the US, if you look at Israel, if you look at Korea, if you look at UK, or even in Germany, you can see that there are elaborate systems which have been set in place to bring about the ecosystem that allows for the transfer of basic research that is done in the laboratory into the industry. So so it's not just, you can't just pin the responsibility on the scientist. We need the government to come in to bring in the regulations, the industry, all of those have to be brought on a platform with the idea that the innovation, because we have to recognize without innovation, without an innovative society, the country cannot progress. So it is in the interest of all to see that this happens. And so how do we, and I'm happy that both at the central government and the state government, there are many initiatives that have been taking place. The Higher Education Council is taking several initiatives to try and improve translation research in medicine. So there are steps taking place, but I think that we need to focus a little bit more on developing that healthy ecosystem if you really want that to happen. It is, you can't, what I'm saying is it's not just purely the responsibility of the scientist. And
when do you think actually we should, when in schools, early schooling and high schools, college, undergraduate studies, and how to make these interventions as effectively as possible to ensure that we have a better science education?
Of course, as early as possible. It's not that you have to teach science at an early stage. Of course, what I would say that there are certain qualities that you require if you really want to be a good scientist. One, of course, is the basic curiosity. So that is what I gave the example of my teacher in Pune. So like that, if a teacher can inculcate a curiosity in a young student, very often if you ask any scientist, I gave you my example, or you ask any scientist, internationally recognized scientist, you ask them, what brought you into science? Like the first question that you asked me, they will say, oh, a school teacher showed me something under a microscope, or somebody showed me something in a telescope. So that instilling and that spark is what actually instigates somebody to follow it up. And then you have an environment which supports you. So I would say that curiosity, if you ask me what are the characteristics that you require for a student to become a scientist, curiosity is one. That is, I would not say that intelligence is so important, because that is something that people talk about and which has really no meaning. Because if you are really interested in something, you will be capable of learning that. And so, but I think one characteristic that is required is courage. Because if you really want to do science, unlike in other fields, you have to have the courage to fail. Because if you want to discover something new, you can't do this because you're not doing something that is already reported in the textbook. You're not, if for example, you're not building a bridge using standard techniques, or you're not doing a surgery following a set of, you are trying to bring something new. And in order to do something new, you have to fail several times. So the courage is something that I feel young scientists, young children should develop. Because very often, if you want to follow your passion, society may not support it. They may think that this is not a practical way of building a successful life. But that is where you have your own passion. How do you actually follow that passion? So I would say curiosity and courage are two very important aspects if you really want to build a career in any field, which is unique from the following the mainstream. And science is away from the mainstream.
Yeah, well, I was actually reading in one of the articles in Current Science a couple of years back. The chemical science is one area which is actually leading in India, for example, compared to other areas. So why do you think?
Again, I think that we have, if you really look at it, we have had
like in terms of publications,
yeah.
the researchers who are the in comparison.
I think
in
overall
terms of
Indian
impact.
science has been doing well. In terms of numbers, I think the chemical sciences has been doing much better. Material sciences, I think there have been a lot of. I think as chemists, people are a little bit more organized. We had people like Professor C.N.R. Rao, Professor M.V. George, P.T. Narasimhan from the founders of the chemistry department in IIT Kanpur, and so that is still, I think that, and prior to that also we had many famous chemists in India. So this and I think they have been able to support a structure which has encouraged a lot of young people to flourish. And if you look at many institutes have had directors who are chemists, and so this role of, I think that is, if I were to pinpoint on something, where a community which nurtures the youngsters to come up. So that is not just focusing on our own career, but focusing on the career of the next generation, helping them to grow and grow above you. That is in the true sense of a teacher. That is what is needed, I think. We have had many examples of such people in the field of chemistry within the country.
And when we talk about science, doing science is expensive. And when we talk about the countries who are actually doing very well in science,
yeah.
You can see the amount of money that in terms of grants the governments have been making to science.
Yeah.
Are you happy with the science funding?
No, I think that of course, as you know, there is room for improvement in that. But again, when you mention something else about the industry and the interaction between the industry and the academia, when you look at all the other countries where you see that a lot of money does come in from the industry. And so in countries like India, where not much of that is happening, you see that the funding that comes from the government ends up in publications or patents. Now that patent, how does it then create wealth for the nation? That is where the translation happens. And that is something that it is in the interest of both the industry and the academia to come together. Unfortunately, we have not seen that happen as successfully here as we would in many of the other countries. So once that happens, then the loop is completed, and so the money that flows out of the government then comes in a multiplied fashion back into the academia, and so that is the ecosystem that I talked about. How do we build up that ecosystem? So it's not just money coming in from the government ending up in terms of publication patents. Those patents have to go out then and make money and bring it back into the system. So once that happens, you will find that because it is in the interest of the government to see that is, as I said, in an innovative nation, in an innovative society. How do we build that? That is what that should be the goal, and it is necessary for the government, the academia, the industry, all come together and recognize this as a common problem for the country, and see how we can build up that necessary ecosystem.
And I was looking at the government policies, the budgetary allocations and all. The government want to have more and more of renewable energy these days because of these carbon issues that which we have, and it appears that there will be more funding for the renewable, particularly solar energy. But how strong are we in terms of making the solar materials, photovoltaic materials and other materials for solar?
That is the very recognition that is given will make the facilities come up. We are reasonably good, but when you compare with countries like China, we are far behind. The infrastructure that is required has to be established, but there is no other alternative. When you talk about alternative energies, if you have to talk about sustainable growth, this is going to be essential, and we have to catch up. And although I know that there is excellent research being done in many of the institutes around the country, and again, come back to the idea of getting that translated. And also developing the infrastructure for building right now much of the components of the traditional solar cells are imported. How do we make those within the country? And so those are things that need to be where we need to catch up. I think we have some ways to go in that in order to be really competitive with the rest of the world.
So what do you say to a new entrant to science?
No, it is, I would say that, it is if you really enjoy a profession where you can follow your own passion, where you can follow upon your curiosity, then it is really a wonderful, because like in any profession there will be hurdles, and there will be there are enough things that you can complain about, but if you really are interested in what you do, then these become part and parcel of the game. You will always overcome those hurdles, and there are many opportunities within the country, outside the country, which allow you to become recognized. But science for me is not like a sprint, it's like a marathon. It's not something that you just make a great discovery and become famous. You have to, as you would have known, many of the discoveries in some lives have come at very late stages in their life. Of course, it can happen earlier also, but it's the kind of effort that has requires courage of conviction, high levels of curiosity and passion, and but if you have all of these, then it can be a very rewarding profession.
There has always been this comment there, the non-scientists doing making excellent scientific discoveries, like we were actually talking about in several areas.
Yeah.
So, is there a stage for that right now?
I mean, those are exceptions, because today, if you want to do modern science, you do need a good level of grounding in your own core subject. Of course, you can interact with other people, but the kind of, for example, you mentioned about the need for a high level of funding, because we need equipment and sophisticated equipment. You need to know the working principles of those instruments. So today, to do science, and also the way science is advancing, it is very difficult to do science on your own. You need to collaborate. You need interdisciplinary kind of
interdisciplinarity.
That is also required. So that who is willing to have somebody from another subject, if he wants to interact with you, he will need you to become an expert in your own field. Otherwise, what value do you bring to that? Okay, so the way the complexity of science and science research is going, it will be difficult for somebody who is not a trained person to come in and contribute significantly to that area. It could always happen. But
yes. Do you really feel that there is too much of a compartmentalization, subject-wise compartmentalization in our educational system?
I feel so. That is something we have to be more open. Even when we see kind of interactions between different disciplines, we see it more at the level of multidisciplinary research, where two different people with different skills use their skills to solve a problem, but they remain experts of their own area. Whereas in interdisciplinary interactions, you try to learn the language of the other person to some extent, and vice versa. So both of you learn, and then you develop a kind of a common language, which eventually evolves into a new discipline.
So interdisciplinarity is not just collaboration.
Yes, if you look at chemistry, the very first photochemistry, photonics and chemistry joins together to form, photophysics and chemistry joins to give you photoresponsive materials. So everywhere you can see, photobiology is another word. If just talking about my own field, photonics, which involves engineering, physics, biology, everything. So interdisciplinary research is necessary, but at the same time, you have to have some core strength in your own area, so you can contribute to these kind of.
Your advice to a career in someone who is looking for a career in science. Finally.
Yeah, as I said, you have to find out what excites you. How do you do that? You have to be curious, because you have to try out many things. It is not easy to find out your area of passion, just area that you're passionate about, just like that. You have to try out many things, and somewhere something will click. You have to read. You have to be a voracious reader, not just science. I would say that you have to be reading all kinds of fiction, all kinds of things. You have to be voracious. That develops a sense of curiosity in you, and that tells you what line that would be of interest to you. Somewhere it will click, and then to have the courage to follow that up. And then look for a good place where you can build up the kind of base knowledge that you require for that. Today in India, we have some very wonderful institutions. Your Calicut University Chemistry Department itself is doing a very good job. You know, we have ICES, we have IIT, so there are plenty of places and opportunities for a young person to go. And as I said, also always be on the lookout for good mentors, because these are people who have had good experience in their life, who are willing to share with you and help you build up your career. And so these and many other ways of follow your passion. And nature, of course, can become a very good inspiration for that if you're really curious to find your niche in science.
Thank you, Professor Das, for sharing these valuable insights and your experience in science, particularly for those who actually want to pursue a career in science. Thank you very much.
Yes, thank you. It's a pleasure.